The Earth's shield is failing, and nobody is safe. Alarms hit all at once. Hubble dropped into safe mode. A CubeSat flatlined mid-pass. Controllers drew a jagged no-go box over the South Atlantic and stood down. Not a storm, not a hack. Space punched through our shield. The weak spot is bigger than a decade ago, and it just split into two lobes creeping toward Africa. Satellites glitch, flights kink routes, grids wait for the wrong night. Why here and why faster now? We'll expose the South Atlantic Anomaly, the deep engine 3,000 kilometers down, and the hard truth. Earth's shield is shifting, and our tech has to keep up. What counts as a failing shield? To understand failure, start with the job. Earth's magnetic field rises from liquid iron churning in the outer core and stretches into space, steering radiation around our planet. When it's strong and well-shaped, the field funnels most high-energy particles toward the poles. When it weakens or warps, particles take shortcuts to lower latitudes and altitudes where our satellites live. Failure isn't a cinematic flip overnight. It's a stack of smaller problems. A rapid drop in regional intensity, dents where field lines sag closer to Earth, and solar storms that bite harder because the shield pushes back less. On the ground, you rarely notice. Ozone governs ultraviolet at the surface, but anything that relies on electrons behaving predictably notices fast. That's the unsettling gap. Daily life feels normal, while the infrastructure behind it inches closer to the edge. Enter the South Atlantic Anomaly, a long-lived weak patch stretching from South America towards southern Africa. In this corridor, the field dips, letting energetic particles skim much lower than elsewhere. Spacecraft passing through see more radiation hits. Hubble surrenders science time every orbit in that sector. The International Space Station rides through spikes that flip bits and trip alarms. Small satellites, light on shielding and redundancy, sometimes never wake after a pass. Engineers call the root problem single event upsets. A charged particle streaks through silicon, deposits charge, and turns a 0 into a 1. No smoke, no scorch, just an inverted command at the worst time. You can defend with error-correcting memory, triple-vote logic, watchdog timers, current limiters, and smarter autonomy. You schedule instrument naps, you avoid reboots in the corridor, you route links outside the hot zone. These moves buy margin. They don't erase physics. As the corridor widens and splits, operators draw bigger boxes on their maps and accept more downtime. Widen the frame to people, planes, and power. A patchier, weaker field makes space weather couple more efficiently to the upper atmosphere. GPS signals can wander during storms, and navigation integrity degrades more often. Airline dispatchers already adjust altitudes and paths during solar events to manage dose and radio blackouts. A deeper anomaly nudges those decisions into latitudes that didn't used to worry. On the ground, long transmission lines and pipelines feel geomagnetically induced currents when the field swings fast. The shield doesn't create storms, it sets the threshold where nuisance becomes damage. So why here and why now? The clickbait headline says the field is dying. It isn't. The truth, Earth's dynamo breathes and sometimes stumbles. At the top of the core under southern Africa, reverse flux patches point opposite the main dipole. They tip surface field lines downward over the South Atlantic and carve the dent we fly through. Above that, the lowermost mantle is lumpy. A huge hot province under Africa seems to steer heat out of the core, bend flow, and stack reverse flux in certain longitudes. Satellites sharpened the picture. In the last decade, the weak region spread, and the minimum intensity fell by a few hundred nanoteslas. And the shocker, the one bruise split into two lobes, west and east, drifting and pulsing out of sync, with the eastern lobe growing toward Africa. This dual-lobe split is the central mystery. It looks like the engine below shifted gears, not random noise. Define failing in human terms. More faults clustered over the anomaly. More instrument downtime baked into plans. More conservative procedures in aviation and grids during storms. And more design budget spent on resilience that used to be free. The shield hasn't vanished. It's become uneven, and modern systems are sensitive to the seams. Understanding the seam demands we go deeper, to the core where liquid metal flows, braids magnetic flux, and occasionally sends a dent to the surface big enough for a space telescope to feel. Forensics at 500 miles, satellites getting punched. Start in low Earth orbit, where routine turns brittle over one swath of ocean. Hubble isn't moody, it's careful. Every 97 minutes, planners watch its track approach the South Atlantic and choreograph the same move. Freeze pointing, close shutters, power down. Sensitive detectors ride it out. Added up across years, and a thick slice of science time gets surrendered to that corridor alone. Survival, not superstition. On the International Space Station, you see the anomaly on a dosimeter before you ever look out the window. Rates tick up through the pass. Laptops stutter. A payload reboots. Crew jokes are polite cover for a simple fact. Avionics grow fragile in that box. Small spacecraft feel the edge even harder. CubeSats ride with thin aluminum-tight power margins and minimal redundancy. The pass comes, a single ion threads a memory cell. The command buffer flips. Sometimes the bird never calls home again. Engineers have a tidy name for this: the single event family. Upsets, transients, and latch-ups. A stray particle slams through silicon, leaves a track of charge, and inverts logic or spikes a line. No burn marks, no drama on the outside, just the wrong bit at the wrong time. You defend with error-correcting codes that vote truth back into memory. You triple-key logic, so 2 good copies can outvote 1 liar. You install watchdog timers that pull a subsystem back from confusion without dragging the whole bus down. You add current limiters, so a latch-up can't cook a board before it clears. You scrub configuration and FPGAs to flip stray bits back before they snarl state. Operations learns new choreography. Don't reboot over the box, don't uplink there. Gate high gain detectors early. Warm optics longer after. Star trackers get smarter firmware that rejects cosmic ray zits. Autonomy rules grow strict, so one sensor twitch can't cascade. It reads like folklore until you tally failure reports and watch the pattern cluster over the South Atlantic. Hitomi made the lesson brutal. The observatory launched clean, started brilliantly, then a bad bit in a guidance path met a known sensor quirk. Thrusters fired when they shouldn't. Spin built. Panels tore. A world-class mission ended. Investigators traced the chain through software, timing, and radiation susceptibility. Nobody hacked anything. Physics threaded the needle, and procedure wasn't ready. What's new isn't that the anomaly exists. Old satellites saw it. What's new is the shape and the cadence. With modern field models, operators watched the weak field footprint stretch and the floor drop. The single bruise became 2 rooms to tiptoe through, western and eastern lobes, drifting and pulsing out of sync. The eastern lobe trends harder toward Africa. For hardware, that splits avoidance into more complicated geometry and longer exposure per orbit. Inner belt protons skim closer under the sag, and secondary showers bloom where they shouldn't. A spacecraft that once spent minutes in the fringe now spends longer under the worst of it. Multiplied by constellations and the math gets cruel. A tolerable annual upset rate per satellite turns into daily events across a fleet. Designers push back where they can. Part selection shifts to higher linear energy transfer thresholds. Layout space critical nodes. Ground testing fires heavy ions through candidate chips and catalogs cross sections. Architectures isolate faults and recover fast. Flight code assumes memory lies and asks twice. Telemetry grows forensic, time-tagged, high rate, with breadcrumbs that let engineers reconstruct what failed and why. Insurers learn the vocabulary. Premiums nudge down for latch-up immunity and scrub rates up for wishful thinking. Even so, you feel the cost. Downlinks slip when receivers reboot mid-contact. Imaging campaigns accept blind strips to protect gain. Radar payloads add warm-up minutes before firing after a hot pass. Autonomy becomes conservative enough to feel slow. The budget that used to buy science now buys margin. You can't cheat the physics, only negotiate. There's a human cadence to the learning. Operations teams live by routine. The anomaly erases complacency. Don't cycle power there. Hold attitude in that window. Delay the patch 1 orbit. Scar tissue becomes checklist. Somewhere, a controller hears silence where a heartbeat should be and writes a new rule, so the next team won't. Zoom out and the pattern points downward. The dense dual lobes are not a whim of altitude or solar season. They mirror deeper changes at the core. The satellite doesn't know mantle heat flow or reverse flux under Africa. It only knows its star tracker glitched over a longitude that keeps misbehaving, and the fix is to plan around a moving target. Meanwhile, the ecosystem adapts. Constellations stagger planes, so not every spacecraft crosses the same hot pixel at once. Shared advisories move like pilot reports. Expect resets crossing now. Mission design tools fold live field models into route planning. Flight directors carry a mental map of invisible weather as surely as airline dispatchers carry jet streams. The South Atlantic becomes part of the vocabulary. You don't ask whether it matters, only how you'll live with it today. And that's the quiet. Pivot. This isn't doom, it's friction. Paid daily in minutes and watts and redundant lines of code. The shield above didn't vanish. It slumped in one place, split in two, and kept drifting. Orbit by orbit, hardware and humans learned its shape, then its new shape. The next step is admitting what the dent is telling us. If it's changing this fast up here, the engine 3,000 kilometers down is moving heat and magnetic flux in ways we need to understand. The anomaly over people, planes, power, and people. While satellites learned the shape of the dent first, the consequences drifted down into dispatch rooms and control centers where routine lives. Airline dispatchers already skim solar indices the way they skim wines aloft. On days when the anomaly deepens and the sun is active, routes kink, altitudes shift, and crews get briefings that read like quiet warnings. Over water, HF radio can fade, messages repeat, position reports lag. The airplane lands, passengers never know. In the ops log, align, static, reroute, dose within limits. The dose piece is measured, not guessed. Aircrew already carry higher cosmic radiation exposure than most people on the ground. Regulations track it, and schedules spread it. The anomaly doesn't turn a flight into a hazard by itself. But when solar protons ride a weaker corridor lower, dispatch adds margin. Eastbound red-eyes slide a few thousand feet, or step south a track, trading fuel for dose discipline. It's not drama, just arithmetic. Navigation feels the dent in subtler ways. When solar storms couple to a patchy field, the ionosphere warps. Scintillation scatters signals, pseudo-range errors grow, and your blue dot jitters. For an airliner on final with augmentation, integrity flags watch the data. If those flags slip, procedures step back to raw data skills pilots still train. Different minima, different cadence, the older muscle memory carrying the load. Survey crews, offshore rigs, and precision farmers already build windows around these hiccups. A wider, deeper anomaly expands those windows across time and latitude. Across town, grid operators watch a different heartbeat. Long transmission lines link distant regions. When the field swings fast, it drives currents into those lines that transformers weren't built to love. Most days, protections chatter and reset. On a hot summer night with tight reserves, that chatter can start a cascade. A weaker, patchier field doesn't create the storm that causes it. It lowers the threshold where nuisance becomes damage, especially in places where entities stretch and budgets stretch further. So utilities add friction to the path. Series capacitors block DC on key lines. Neutral grounding resistors tame saturation. Geomagnetically induced current monitors alert operators to derate before heat and harmonics pile up. And they drill black start, the choreography for turning a cold, dark network back on. So the worst day is also practiced. Pipelines feel the same physics drawn in different ink. Cathodic protection fights corrosion by pushing the right current the right way. Space weather adds noise. Operators adjust set points, automate responses, and accept that a few more days per year will feel fiddly. Railway signaling can glitch under fast DBADT. Systems default to safe. Telecom sites add holdover clocks, so a jittery GNSS day doesn't ripple through timing for an entire region. None of this makes a headline. It makes the lights stay on and the calls go through when the sky is noisy. There's a systemic irony that operators know in their bones. The anomaly is regional, the ripples are not. A flipped bit over the South Atlantic delays a weather model ingest, nudging a forecast that nudges a hub bank, moving megawatts by inches at the wrong hour. A line trips in one grid and tie lines hum harder in another. Complexity amplifies what physics starts, and the fixes travel the same networks. So the playbook grows up. Airlines fold radiation and GNSS integrity into dispatch tools, not as exotic flags, but as tiles next to winds and turbulence. HF gets a SATCOM fallback pre-briefed. Cabin crews see dose advisories without drama. Airports rehearse GNSS-degraded ops until calling for a localizer feels like normal, not nostalgia. Grids write staged policies tied to space weather alerts. Defer maintenance, hold reactive margin, watch specific corridors. Pipelines' control rooms accept that their cathodic protection graphs will wiggle and automate the response. Ports with cranes and pilots facing tricky approaches coordinate windows around the same sky. The public peace is modest and honest. Magnetic weather is not apocalypse. It's another forecast. Watch, warning, actions. The message sounds like hurricane season because the behavior should match. Harden where it matters. Stage resources before the window opens. Accept inefficiency on the days that pay it back. Underneath the procedures sits humility. A hot province at the base of the mantle. Doesn't ask for permission. It steers heat. The core adjusts. The field above sags in 2 rooms, and a dispatcher in Sao Paulo changes a flight level. The connection is long, quiet, and real. We won't fix the engine. We'll learn its moods, measure them, and fold them into the way we fly, wire, and schedule. The dent isn't destiny, it's a constraint. Good operators live on constraints. Inside story, how Earth makes a magnetic field. To understand why satellites get punched over the South Atlantic, you have to stand, at least in your mind, 3,000 kilometers down, where liquid iron moves like a slow river wrapped around a solid inner core. Motion in a conductor makes electric currents. Currents build magnetic field. That field threads the fluid and pushes back on the motion. It's a feedback loop called a dynamo. Keep the flow vigorous, and the loop sustains itself. Choke the flow or reorganize it, and the field above changes shape. Sometimes gently, sometimes enough to leave a dent you can fly through. What powers the churn isn't one engine but a stack. As the inner core grows, iron crystallizes and releases heat and light elements into the outer core. That buoyancy drives convection. Radioactive decay adds background warmth. Rotation twists rising and sinking fluid into columnar rolls, aligned roughly with Earth's spin. Those rolls, jet-like sheets and plumes, carry magnetic flux the way wind carries clouds, bundling it into ropes and sheets, shredding it, reassembling it, always moving. From space, you see a tidy dipole like a bar magnet. From the core's perspective, it's weather. The lid on the pot matters. The lowermost mantle above the core is not uniform. It drains heat unevenly across longitudes. Where the mantle is cooler, heat escapes faster, and convection strengthens below. Where it's hotter, heat leaks more slowly. Flow diverts, jets bend. Over Africa sits a continent-scale province of hot, possibly compositionally distinct mantle. That blanket changes how and where the core can shed heat. The core listens and responds. Jets sharpen along some rails, stall along others. Magnetic flux piles up here, thins there. At the top of the core, you can map spots where the radial field points opposite to Earth's main dipole. Those reverse patches are clues to how the flow is steering the field. Link that to what we feel in orbit. When reverse flux gathers under the South Atlantic sector and migrates, surface field lines tilt downward. The field above weakens locally, lowering the altitude where trapped particles skim. That's the South Atlantic Anomaly's shape, written by Deep Flow. The recent split into 2 lobes, western and eastern, tracks with how reverse features at the core mantle boundary slide past each other like weather systems, leaving 2 rooms of weak field at the surface instead of 1. How do we know any of this if we can't go there? We infer with discipline. Satellite missions map the magnetic field in exquisite detail. Ground observatories record the slow drift, secular variation, decade after decade. Models subtract crustal magnetization and ionospheric currents to isolate the core field. Mathematicians invert those measurements to estimate the pattern of field at the top of the core. Seismology, meanwhile, images the mantle's slow structures, where independent lines point to the same geometry: hot mantle under Africa, altered heat flux, reverse core surface patches, and a South Atlantic dent overhead. It stops reading like coincidence and starts reading like causation. The dynamo's sensitivity is the point. It's not a clock, it's a fluid machine with memory. A jet strengthens, advex flux across a boundary, and the surface field over an ocean sags a little more. A plume wanes, new flux emerges elsewhere, and the sag relaxes or moves. None of this requires the global dipole to be failing. Globally, Earth's dipole has eased since the 180s, but the South Atlantic dip is regional and faster. Both can be true because the field is layered. A dominant dipole plus migrating non-dipole patches that pack a local punch. Rotation imposes order, but turbulence adds mischief. Imagine elastic threads, the field lines, stitched through the fluid. Shear stretches them, reconnection snaps and reties them. Bundles drift like storm bands. Where bundles converge in reverse direction, they seed those flux patches that matter at the surface. Where the mantle above acts like a warm lid, flow pathways reroute. The African province's edges, in many simulations, behave like rails guiding jets. It's at edges where contrasts are steepest that flow organizes and flux concentrates. The surface sees the edges as boundaries between rooms of weaker and stronger field, drifting in longitude at humanly inconvenient speeds. There's comfort here. A responsive dynamo is a healthy one. The very changes we dislike in orbit prove the engine is alive and coupled to the planet above it. The risk isn't that the field disappears, it's that our systems run closer to the seams where the field is odd. The deeper lesson is practical. Treat core weather like any other forecastable hazard. Keep measuring. The satellites and observatories are our eyes. Keep modeling. The inversions are our maps. And keep designing with the fluidity in mind, because the core will keep moving heat along the paths the mantle allows, and the field will keep answering in patterns that matter to hardware, pilots, and grid operators. The core mantle conspiracy. Africa's deep blob. Follow the heat to the base of the mantle. Seismic maps reveal 2 megastructures where quake waves slow. One is under the Pacific. The other sprawls beneath Africa and the South Atlantic. They're called LLSVPs. Huge hot piles perched on the core like heavyweight blankets. Not magma oceans. Solid, but hotter or denser than what surrounds them. That uneven lid changes how the core dumps heat. The dynamo below is sensitive to its lid. Cool mantle above? Heat escapes fast and flow strengthens. Hot mantle above? Heat leaks slow and flow bends. Put a hot lumpy province under Africa and you skew the engine. Jets sharpen at its edges. Plumes bend. Magnetic flux gets pumped into different longitudes. At the core's top, we map reverse flux patches. Local spots pointing opposite the main field. In the African sector, they grow and migrate. At the surface, the field sags. That's the South Atlantic Anomaly. Now the world-altering part. Independent lines agree. Seismic tomography draws the African blob. Satellite and ground data inversions show reverse patches marching under southern Africa and the mid-Atlantic. Surface maps show a single bruise splitting into 2 lobes, east and west, out of sync, with the eastern lobe leaning toward Africa. Numerical dynamos that feed in mantle-style heat patterns recreate the same thing. Atlantic low spots, reverse flux under southern Africa, and surface lows where the mantle lid is hottest. Different tools, same longitudes. That's not coincidence. That's a chain. Edges do the damage. The blob's margins look steep, with ultra-low velocity zones that may be extra hot or iron-rich. In models, those edges act like rails. Core jets ride them, pile up flux, then peel off where gradients change. Put one reverse patch along the African edge and another under the mid-Atlantic, and you inherit 2 weak field rooms at the surface. That explains the split and the drift. As those reversed features slide beneath, the rooms wander in longitude. That dual-lobe split is the central mystery and the smoking gun. How stable is this deep blob? Big picture, long-lived. At the edges, lively. That's exactly where flow organizes and flux concentrates. So a persistent macro driver with active rims is the recipe for repeat magnetic weirdness over Africa and the South Atlantic. Surface rocks back it up. The Tristan da Cunha hotspot trail points to a deep source tied to the blob's crown. The South Atlantic Rift followed ancient sutures that now bracket the anomaly's footprint. African lavas and nearby islands record recurring low-intensity intervals in the same longitudes. North African archaeomagnetic curves show bursts of rapid change. The crust isn't steering the core, it's keeping score. Bottom line, the African blob doesn't cause the anomaly on its own. It sets the stage. The core is the engine. The mantle is the throttle and steering. In the last decade, weak field area grew, the minimum deepened, and one bruise split into two. At the same time, reverse flux converged under the hot longitudes. The alignment is too tight to ignore. Planning takeaway. The Atlantic Hemisphere is a preferred stage for magnetic weirdness, long-term lows, and lively variation. Not doom, a noisier baseline. Budget more margin. Treat drift as a feature, not a surprise. The hand on our satellites sits 3,000 kilometers down, hot at the edges. And it's not slowing down. Ancient receipts. Tree rings, ice cores, and magnetic rocks. Want proof the shield matters? The planet kept receipts. Trees shout. In 774 to 775 and 993 to 994 CE, tree rings worldwide spiked in carbon-14. Those Miyake events mean high-energy particles flooded the sky and made extra neutrons. The trees recorded it. Ice remembers. Greenland and Antarctic cores hold layers rich in beryllium, tin, and nitrates, cosmic ray fallout. Some layers match the tree spikes. Others trace stormier decades. It doesn't mean the field vanished. It means when the magnetosphere slackened or the sun surged, the chemistry of the air changed enough to leave marks. Clay tells stories. When ancient pots were fired, iron grains aligned with Earth's field of that moment and froze it in. Later, archaeomagnetism reads the direction and strength. Across the Levant, North Africa, and Europe, you see calm stretches broken by fast swings. In North Africa and the Middle East, some swings are sharp, regional quirks that rhyme with today's Atlantic sector oddity. Now the big stumble. About 41,000 years ago, the Lachamps excursion dragged the dipole down to maybe 5 to 10%. Polarity briefly flipped and snapped back in centuries to a millennium. Lavas captured wild directions. Sediments traced a global reshuffle. Ice cores show isotope spikes. The cosmic ray gate opened wider. Models suggest more nitrogen oxides, some ozone thinning, more UV at the surface. Not an apocalypse. People and ecosystems kept going. But a stress test you'd feel if you flew satellites or needed flawless navigation. Between spikes and stumbles sit lesser dips. Mono Lake, Gothenburg. Sediments show kinks. Paleointensity sags. Isotopes nudge up. The pattern, the dynamo stumbles often enough to matter. When it does, cosmic weather talks louder. The Atlantic won't drop the theme. Basalts from Tristan da Cunha and nearby islands erupted during weak field windows and carry low paleointensities. Seafloor stripes hide subtle asymmetries that, even after corrections, hint at intensity differences in the same longitudes that host today's dent. The crust isn't causing the anomaly, it's keeping the journal. What does it add up to? Comfort and warning. Comfort. Even in Lachamps, Earth kept air, water, and life. Warning. Our weak point is tech. Weak field corridors let in more radiation right where we stack satellites, navigation, and long wires. Scale check. Tree ring spikes are one-year punches. Ice core decades are storm seasons. Excursions are century-scale weak phases with messy geometry. Reversals smear over millennia. Today's dual-lobe over the South Atlantic is none of those extremes. It's a regional sag with a deep driver growing and splitting on decadal beats. Satellites can track it, operators can plan for it. The practical lesson, the past, sets expectations. A living dynamo throws odd years and odd centuries. When the field thins regionally, space weather talks louder. When it thins globally, the sky changes without ending the world. Read the ledger in wood, ice, and fired clay, and build margins that respect a shield made for lungs and lichens, not for silicon and copper. The big fear, pole reversal versus excursion versus doom. This is where headlines get loud, so let's sort the buckets. First is the life we're in now, secular variation. The core's flow rearranges magnetic flux over decades, the global dipole eases a few percent per century, and regional dents like the South Atlantic Anomaly deepen and drift. Compasses don't spin, they wander slowly. Satellites feel more radiation over specific longitudes. Operators respond with procedures and parts. It's noisy, it's manageable, and it's the backdrop for everything else. Next comes an excursion, the stumble with teeth. The dipole weakens hard, often to a sliver of its usual strength, and the geometry of the field tangles for centuries or less. Poles migrate far from their typical homes. Sometimes the polarity briefly flips, then snaps back. Last jumps around 41,000 years ago is the case study. Cosmogenic isotopes spiked, auroras wandered to low latitudes, ozone likely thinned some, and more ultraviolet reached the surface. It wasn't extinction, it was a stronger amplifier. If we'd flown satellites then, we'd have lost a lot of nights and redesigned quickly. Finally, a full reversal, the long dance. Polarity switches and stays flipped for hundreds of thousands of years, but the process is smeared over millennia. Strength sags and recovers in chapters unevenly by region. The fossil record doesn't pair reversals with mass extinctions. The atmosphere doesn't blow off. Life keeps going. For a civilization built on electronics, a multi-century weak phase means chronic friction. More satellite faults, more radio blackouts during storms, more grid precautions, more navigation days that step back to older skills. So where are we? Not in a countdown to a Hollywood flip. Modern models show reversed flux patches migrating beneath, southern Africa and the mid-Atlantic, and a dual-lobe anomaly at the surface that tracks that movement. The global dipole has eased since the 180s, but it sits far above excursion-class lows. The pattern reads as vigorous secular variation plus a regional sag, not a committed plunge. Could an excursion emerge from the same dynamics without much warning? Yes. Excursions in the record don't preface themselves with centuries of trailers. They materialize from reorganized flow, flux gathered, jets rerouted, and the signal at the surface crosses thresholds fast on human scales. The timelines matter. Design cycles and budgets live in 5 to 10-year windows. Grid upgrades land in similar beats. Excursions unfold in centuries to less. Reversals take millennia. That mismatch is the anxiety. We don't need prophecy. We need posture. Satellites sit at the top of the risk stack because they live inside the problem. A patchier, weaker field expands the real estate where high-energy particles intrude. Upsets climb, downtime grows, selective hardening and smarter autonomy buy back time. Navigation sits in the middle. Ionospheric weather gets rowdier when storms couple into a ragged field. Integrity flags do their job. When they slip, procedures take over. Grids feel the field through long conductors. Lower strength and faster gradients lower the threshold where geomagnetically induced currents become trouble. Serious capacitors, grounding tweaks, and conservative operations hold the line, but the nuisance budget grows. The human health picture is more local and honest. Ozone governs ultraviolet at the surface. A dented magnetosphere doesn't sunburn a city. Aircrew dose planning gets sharper during solar particle events and in corridors where particles ride lower. Regulations track it and dispatch adjusts. The biosphere handled last champs and lesser wobbles. Our fragile species is silicon. Geography is destiny for a while. The Atlantic sector has warned magnetic oddities more than once, and the eastern lobes drift toward Africa is today's proof. That shifts operational weirdness toward those longitudes first. More avoidance minutes in orbit, more GNSS hiccups on some days, more grid advisories on moderate storms that used to feel minor. Then the engine reorganizes and the stage moves. What about headline-grabbing ideas, inner core rotation changes forcing flips, sudden switches, end-of-world talk? Interesting research lives at the edge. Reality lives in evidence. The hand we can see is the Mantle's heat pattern steering core flow. Decadal maps show the dents forming before hardware feels them. That's enough to plan against, so the fear shrinks when the plan fits the clock. Treat core weather like hurricane season. Forecast the dents with satellites and observatories. Harden where it pays. Write rules that assume memory will lie and timing will slip on the wrong nights. Accept inefficiency on the days that buy resilience. If an excursion ever announces itself, it will be in the math first, not the movies, and the playbook will already be open. The clock, how fast the shield is changing now. Think of the field as a heartbeat. You can only hear from space. Since the 184s, the global dipole has eased downward by roughly 10%. That number isn't a cliff, it's a drumbeat. The drama hides in the regional curves. Over the South Atlantic, the weak field area has grown. The minimum intensity has slipped a few hundred nanoteslas lower, and what once mapped as a single bruise now resolves into two lobes drifting and pulsing out of sync, with the eastern lobe edging toward Africa. This is not noise, it's organized change. You can plot year to year, the cadence is decadal. You don't watch the dent deepen in a weekend, you watch contour lines on updated field models ball farther inward every few seasons. Flight dynamics teams feel the change as larger avoidance polygons, longer safe mode windows, stricter autonomy gates. Grid operators see it as a slightly higher coupling factor folded into next winter's playbook. Surveyors and offshore rigs experience more windows of GNSS scintillation creeping into latitudes that used to be quiet. The clock you meet isn't prophecy, it's scheduling. Behind those contour lines sits a moving engine. Core surface inversions stitched from satellite and ground data show reverse flux patches sliding beneath the Atlantic sector. An African feature marching west, a mid-Atlantic sibling inching east. Between them, the surface dents stretch, split, and drift. Watch those maps as a flipbook, and you can almost see the hand sketching the anomaly from below. It makes the dual-lobe geometry feel less like a curiosity and more like a forecastable pattern. How fast is fast enough to matter? For hardware in orbit, a few hundred nanoteslas of local weakening across a decade lowers particle mirror points, pushes trap populations closer to operational altitudes, and lengthens per orbit exposure by minutes. Multiply by thousands of spacecraft, and those minutes become daily scrubbing, weekly lost passes, and monthly anomaly reviews that read like weather reports. For navigation, more frequent ionospheric disturbances riding a patchier field mean integrity flags, blinking a little more often. The procedures don't change, their duty cycle does. Could this be the prelude to an excursion? The honest answer is that excursions in the record didn't mail invitations centuries ahead. They emerged from the same kind of reorganized flow we're tracking now. Today's global dipole sits far above excursion-class lows, and the observed changes look like vigorous secular variation, plus a regional sag with a deep driver. That answer is unsatisfying and useful at the same time. It won't sell a headline, but it will steer a design review. The near-term horizon is where this clock matters most. Mission planners don't live on millennia. They live on 5 to 10-year windows. Field models updated annually with near-term projections. Let operators draft avoidance calendars, not just for a generic anomaly, but for 2 drifting rooms, each with its own beat. Airlines can fold expected GNSS integrity dips into seasonal routing guidance. Utilities can tie staged operating policies to space weather alerts, knowing their threshold is lower than it used to be. Pipelines can automate cathodic tweaks, and telecom networks can audit time holdover at edge sites so a jittery day doesn't ripple into a region. The tick you can trust isn't a countdown, it's a ratchet. More frequent satellite faults clustered over the anomaly unless designs buy back immunity. More instrument downtime budgeted up front because it's cheaper than surprise. More grid advisories on moderate storms that used to be shrugged off. More days when survey crews shift windows, and more approaches flown with old skills when integrity slips. None of it is spectacular, all of it stacks. There's one more tempo worth marking. Measurement cadence equals management cadence. Satellites mapping the field, ground observatories logging drift, and models that separate crust, ionosphere, and core build the only clock that matters. When that clock ticks annually instead of sporadically, avoidance shapes can be drawn before hardware crosses them. When funding lapses and data goes stale, planning reverts to folklore. The field will keep changing at its pace. Our job is to keep the maps breathing at ours. So set expectations low on drama and high on specificity. Expect the eastern lobe to lean harder toward Africa in the near term. Expect the weak field area to grow modestly, not explosively. Expect operators to treat the anomaly less like a place and more like a moving schedule constraint. And expect the heartbeat to keep sounding like this. Not a siren, but a metronome that, if you listen closely, tells you exactly how to stay in time. Building resilience, space weather, era playbook. If the engine under Africa won't steady, we steady our side. Start with spacecraft, because they sit inside the problem. Design shifts from hoping bits behave to assuming they won't. Memory gets error-correcting codes everywhere. Critical state is triplicated, so 2 clean copies can outvote a liar. Configuration in reprogrammable logic is scrubbed constantly, so stray flips don't accumulate into tangled logic. Power rails get current limiters, so a latch-up can't cook a board before it clears. Watchdogs reset only the misbehaving limb, not the whole body. Star trackers learn to ignore cosmic ray freckles. Gyros carry attitude when optics blink. Architecture matters as much as parts. Boxes are partitioned, so a fault can't cascade across domains. Telemetry runs at higher cadence with time tags and breadcrumbs, so engineers can rebuild the moment a glitch began. Flight software assumes sensors will lie. It asks twice, cross-checks, and refuses single-point truth. Autonomy rules tighten. No reboots in the dent, no uplinks there, gate-sensitive instruments early, warm long after. Route planning goes from simple orbits to calendars. 2 moving rooms over the South Atlantic with beats of their own. Constellations stagger planes and local times, so not every satellite crosses the hottest pixel at once. Selective hardening replaces fantasy. You don't gold-plate everything. You harden the brain, the power spine, and the radios that bring a mission back after a bad pass. You test ruthlessly with heavy ions and protons, build upset cross-sections, and show your math. Insurers notice. Premiums shift when latch-up immunity and scrubbing rates grow up, and when operations prove they'll wait one orbit rather than roll dice in the box. Aviation writes quieter rules with the same spine. Dispatch folds solar indices and GNSS integrity tiles next to winds and turbulence. On active days, routes kink or step down. HF radio gets SATCOM fallback ready before crews ask. Dose advisories become routine housekeeping rather than drama. On approach, augmentation. Integrity flags are watched as closely as minima. When integrity slips, procedures step back to raw data skills pilots still train. Different minima, different cadence, no surprise. Airlines track cumulative dose for crews honestly and spread it. They treat the anomaly like mountain weather. Forecastable, avoidable, not theatrical. Grids add friction where physics bites. Series capacitors on long east-west lines block geomagnetically induced DC. Neutral grounding tweaks tame saturation, and substation monitors watch for slow drifts that precede heat and harmonics. Operators carry staged policies tied to alerts. Defer non-essential maintenance, hold reactive margin, derate specific corridors when D-Bay DT climbs. Black Start is rehearsed until it's choreography rather than legend. Pipelines automate cathodic protection adjustments, so corrosion math stays honest when the sky shoves current the wrong way. Rail signaling defaults safe when noise rises. Telecom networks add holdover clocks at edges, so a jittery GNSS day doesn't ripple across a region. Forecasting becomes connective tissue rather than an afterthought. Spacecraft at L1 watch the solar wind. Coronagraphs flag eruptions. Models push cones and arrival times. Ground magnetometers, ionosons, and GNSS scintillation maps translate global alerts into local risk. Field models updated with satellite and observatory data project, near-term lobe drift, so avoidance calendars are written before hardware crosses the lines. Dashboard stops saying angry and starts saying, this corridor widens by 15 minutes tonight. Derate these 3 lines. Expect more scintillation between these latitudes after dusk. Policy forces memory into procurement. Spacecraft classes get latch-up immunity thresholds and scrubbing requirements. Airline regulators harmonize dose reporting. Transformer specs adopt GIC withstand criteria by default. GNSS integrity thresholds tie to operational gates, so procedures step cleanly rather than improvise. Data stops living in PDFs. Field models, magnetometers, and ionospheric nowcasts expose APIs, so flight planning, grid EMS, and pipeline, SCADA, pull them into daily tools. Public agencies talk plainly. Watch, warning, actions. People don't need metaphors. They need the 3 things they can do. Culture carries the hard part. We renormalize margins. A decade of free safety has gone over the South Atlantic and thinning elsewhere. We trade a little efficiency for slack. Longer warm-ups, more cross-checks, a few more minutes of non-science time, a bit more fuel, a slightly lower line loading, a backup clock that seldom earns applause. It feels like loss until the night it isn't. Measurement cadence equals management cadence. The swarm era proved what continuous mapping can do. Successors need funding before the heartbeat goes dark. Ground observatories keep the long baseline honest. When models breathe yearly, avoidance calendars stay specific. When budgets blink, folklore returns, and folklore is expensive. None of this is heroics. It's plumbing and posture. We won't flatten the dent. We'll route around it, harden just enough and make magnetic weather another forecast professionals fold into their day. That's resilience at human speed. Not perfect certainty. Predictable, practiced inconvenience that keeps missions alive, flights on time, grid stable, and quiet rooms unremarkable when the sky gets loud. Geological echoes, Africa, South America, and a magnetic odd couple. Before the Atlantic opened, Africa and South America were one piece, sharing roots, sutures, and deep plumbing. When rifting split them, it didn't just draw a coastline, it tore through a magnetic neighborhood that had been odd for a long time, and the rocks kept the receipts. Along those newly minted margins, the Tristan da Cunha hotspot left a scorched breadcrumb trail. Its basalts carry geochemical fingerprints that point to a deep source consistent with the African low-shear province we've been following. Surface scars, deep heat, same stage, same longitudes. Look at the breakup lines. The South Atlantic didn't unzip randomly. Rifts chased older weaknesses, ancient sutures in the crust. Those scar lines now bracket the modern anomaly's footprint. As ocean crust spread, it froze polarity reversals into stripes like a barcode. Those stripes run clean, but their amplitudes aren't perfectly symmetric. When you correct for spreading rate and sediment load, subtle differences remain that hint at hemispheric intensity asymmetries right where today's dent lives. Not proof by itself, context stacked on context. Move inland. On the Brazilian side, the São Francisco Craton's volcanics include lavas whose paleo-intensity runs systematically low during particular windows. Across the gap, southern Africa's lavas show their own lean periods. Archimagnetic curves from North Africa and the Levant record, bursts of rapid secular variation biased to these longitudes. You don't need every site to agree. You only need the trend to return often enough to stop calling it coincidence. The hotspot trail tightens the link. Tristan da Cunha's plume taps deep mantle near the African LLSVP's crown. That chemistry passes upward through time, tying surface volcanism to a persistent thermochemical engine at the base of the mantle. If that engine also steers core heat loss, you've got a vertical chain. Hot blob, skewed heat flux, core flow bent, reversed flux patches, weak field rooms at the surface. Rocks can't see the core. They can tell you they keep erupting above the same hot basement that, in models and inversions, lines up with magnetic oddities. None of this means crustal magnetization pulls field lines down. At satellite altitudes, crust is a rounding error compared with the core's contribution. But the crust is a diary. Brazilian ceramics fired in Roman-era kilns lock in directions and strengths that, when strung across centuries, show local bursts and lulls. On Tristan and nearby islands, paleo-intensity estimates from different epochs shade lower than a tidy dipole would predict. In southern Africa, paleomagnetic stacks reveal fast directional swings that echo the restless field we track today. Separate lines, familiar song. Plate reconstructions add another nudge. When you wind continents back to their pre-rift fit, the anomaly's modern footprint spans a single coherent corridor. Shift forward again, and that corridor straddles two continents that inherited a common deep context despite drifting apart. If the African LLSVP's macro pattern persisted, whoever sat above its edges, then and now, would see livelier non-dipole behavior. The South Atlantic chose them both. Field workers feel the pattern without needing the theory. Sampling campaigns on Tristan Hall basalt blocks that carry low field signatures. Labs build intensity curves with more troughs than you'd expect from a calm dipole. In North Africa, pottery sequences show jumps fast enough to make navigators of the past grumble, if they'd had compasses. Offshore, the seafloor's magnetic stripes, when handled carefully, whisper the same asymmetry. The swarm era lets us lay those whispers next to a moving map of the anomaly and watch the rhyme play out in modern time. Here's the meaning operators can use. Regions under long-favored longitudes aren't cursed, they're inheritors. Expect a noisier baseline, a few more procedures on a few more days, a mission plan with a wider no-go box in a particular band of orbits, a grid policy that treats moderate storms as worth attention. Expect the dense rooms to drift because the rails deep below are edges, not anchors. And expect the rock record to keep adding pages that read like this one, because a living planet leaves patterns on its way to tomorrow. Myth-busting, facts versus hype. Field not dying. The field isn't ending civilization. Global strength has eased since the 1800s. Regionally, the South Atlantic is dented and split. Real, but manageable with design and procedures. Stay-lights do fail here. Yes, Hubble schedules safe windows. ISS logs spikes. CubeSats disappear. It's a weak corridor where particles ride lower. Error correction, scrubbing, current limiters, and smarter autonomy buy back margin. The calendar now has 2 moving rooms over the South Atlantic. No, UV won't fry cities. Ozone sets surface UV. Health risk is at altitude and in orbit. Aircrew, dose planning, and satellite parts budgets. On the ground, you feel it indirectly. Timing, grids, aviation, logistics add wait 1 orbit and hold margin tonight. Grids feel it. Fast field changes drive currents in long wires. The fix isn't bunkers. It's series capacitors, grounding tweaks, dB/dt monitors, stage policies, and black start drills that make the worst night boring. Not from 5G. The anomaly isn't antennas or anything we built. It's core flow, steered by deep mantle structure under Africa. Fingerprints, reversed flux patches, long-lived non-dipole minima, 2 drifting lobes. Nav stumbles. Some days, storm-coupled ionosphere plus a patchy field means more scintillation and integrity flags. The fix. Multi-constellation, multi-frequency, honest integrity thresholds, and crews who keep raw data skills sharp. No countdown to flip. Reversals take millennia. Excursions can be centuries or less without mass extinctions. Today looks like vigorous secular variation plus a regional sag. If an excursion comes, it shows up in the math and procedures first, not in headlines. Dual-lobe is real. The weak area is growing modestly. The minimum deepened by a few hundred nanoteslas. 1 bruise split into 2 lobes out of sync. Eastern lobe leaning toward Africa. This split is the central mystery and a planning anchor. Not the crust fault. Crustal magnetization isn't pulling the field down at satellite altitudes. The crust is a diary. Lava, ceramics, and stripes show how the field behaved, especially here. Archive, not driver. Resilience is unglamorous. Spacecraft assume memory will lie. Airlines fold radiation and integrity into dispatch. Grids add friction. Pipelines tune cathodic protection. Telecoms add time holdover. Forecasts become actions. The win is a non-event, not nothing to see. The engine is alive. It sends headaches to a world wired tight. Pay attention. Fun measurement. Keep posture, not panic. Treat the 2 drifting rooms like weather. Spend a little efficiency to buy a lot of calm. The next 10 to 20 years, scenarios you can plan for. Start with the baseline. No fireworks, just the trend lines continuing. The South Atlantic dent keeps widening modestly and deepening a little. The 2 lobes keep drifting like slow storms, and the eastern one leans closer to Africa. Global dipole strength slides a few more percent at most. In orbit, avoidance calendars lengthen by minutes per pass, scrub rates tick up, and autonomy rules grow stricter. That feels like friction, not crisis. You pay it as routine, a lost downlink here, an instrument nap there, a firmware patch that refuses to reboot in the box. In that baseline, spacecraft design codifies what smart teams already do. Error correction everywhere, scrubbing continuous, current limiters on critical rails, and no power cycling rules bound to longitude windows that match the lobes. Constellations stagger planes and local times, so not every satellite trips the same hot pixel. Star trackers carry hit rejection as default. Gyros bridge attitude when optics blink. Mission proposals show upset cross-sections the way airlines show fuel reserves. Insurers reward hard numbers. Budgets accept selective hardening as the price of science. Aviation adapts in software and muscle memory. Dispatch tools blend solar indices, GNSS integrity, and field model projections into the same screen as winds aloft. HF fades get an automatic SATCOM fallback. Long-haul doses are forecast and spread. Tracks kink without drama when solar protons ride corridors lower. On approach, integrity flags stay honest. When they slip, procedures step back to raw data skills and nobody blinks. Surveyors and offshore rigs widen their windows for scintillation and keep productivity by scheduling, not by faith. Grids add quiet safeguards. Series capacitors land on long east-west lines that underperform on storm nights. Neutral grounding tweaks tame saturation. Substations gain geomagnetically induced current monitors tied to stage policies. Defer non-essential work. Hold reactive margin. Derate named corridors when alerts arrive. Black start drills run to cadence, not legend. Pipeline controllers automate cathodic tweaks. Rail signals default safe. Telecom adds more holdover clocks at edges, so a jitter day doesn't echo through a region. The public hardly notices. The meter does. Now layer a stormier stretch, 2 or 3 solar cycles where active years pile up. The dent hasn't caused it. It makes the bite sharper. Satellite anomaly logs thicken. Not catastrophically, but enough to turn weekly reviews into daily habits. Some older buses of marginal immunity retire early. A few CubeSats die in clusters. The rest skate by because designers assumed memory would lie and planned the exits. Integrity flags blink more often. Approaches step down more days. Survey crews shuffle calendars and still deliver. Grids treat moderate alerts like yesterday's strong ones. Power stays on because the playbook got boring. Run an outlier. A Miyake-scale solar blast arrives during an eastern lobe deep phase. Spacecraft drop to defensive crouch. Gated detectors, scrubbers racing, autonomy boxed tight. A handful of lightly protected platforms fail. Headlines flare. Operators publish after-action reports that read like checklists. GNSS outages go regional for hours. Procedures carry the rest. Airports look dull because practice won. Grids with series capacitors and stage policies ride it out. A few aging transformers complain and get retired in daylight. The story ends in reports, not documentaries, because enough people rehearsed. Geography shapes the human map. Africa and South America feel the eastern lobes drift first. More avoidance minutes for satellites overhead. More grid advisories on storm nights. More days when GNSS integrity nibbles into schedules. That nudges investments. More series capacitors in long inner-Ts. More training for GNSS degraded ops at busy airports. More holdover in telecom networks. Regional insurers price evidence, not fear, and premiums reward preparation. The narrative moves from why us to what's our margin, exactly where it belongs. 10-year procurement cycles meet decadal field change head-on. Funding sustains continuous mapping, swarm successors, and dense ground observatories, because models breathing yearly become operations breathing daily. The tools evolve. Near-term lobe drift projections push directly into flight dynamics, dispatch, and grid EMS screens. Alerts stop saying angry and start saying specifics. Widen this corridor by 15 minutes. Hold margin on these 3 lines. Expect more scintillation between these latitudes after dusk. APIs replace PDFs. Folklore drains out. Culture closes the gaps. Organizations normalize inefficiency that buys resilience. A few more warm-up minutes, a little more fuel, slightly lower line loading, a backup clock nobody glorifies. Design reviews assume drift continues and budget for it. Mission planners draw 2 moving rooms, not 1. Grid planners choose transformers with honest GIC withstand. Airlines keep raw data skills vivid. Public briefings use the same cadence as storm season. Watch, warning, actions. People learn the 3 things they can do, then get on with their day. The long risk many worry about, an excursion, remains a possibility without a countdown. If it arrives in our planning window, the transition looks like more of the same, only intensified and prolonged. More particle access at lower altitudes, more GNSS days stepped down, more grid nights staged, more satellites designed like they mean it. No siren, just a louder metronome. The meaning of the next 20 years is simple. Keep the maps breathing, let models talk to operations, buy margins where they pay, and treat core weather like any other forecast that good operators quietly outwork. Meaning, fragile tech on a wild planet. Earth's shield was built for breath and bones, not for firmware and fiber. For most of history, good enough meant lungs could fill and forests could grow. Our tech bets on single bits and tight timing, things the planet never promised. One particle hits at the wrong microsecond, and a spacecraft naps. The same particle hits a tree and nothing happens. That mismatch isn't failure, it's scale. So change the question, not why is the field doing this, but why do we build systems that need it to be simple? We chase speed, precision, and efficiency, until the slack vanished. Cheap orbits, tight line loading, navigation glued to a blue dot. It worked, until the dent widened into 2 rooms and sent the bill. The fix isn't heroics, it's respect. Redundancy beats elegance when the sky is fickle. A few microamps of current limit can save a mission. A few minutes of margin can save a grid. A dispatcher can carry dose and GNSS tiles next to winds without turning it into theater. It takes humility to trade efficiency for slack. It takes craft to do it quietly. Listen to the planet. The African deep blob isn't a villain, it's the boundary. The core moves heat along rails, the field sags where those rails lead. People draw boxes on maps and write rules. That chain isn't tragic, it's beautiful. A living engine, a measurable response, and a culture learning to listen. Separate fear from scale. A reversible dent isn't a plot twist. 10% dipole easing over 2 centuries is context, not collapse. The real risk is local and human. More upsets, more scintillation windows, more nights when lines hum. Those are engineering problems. The danger is pretending the free safety we enjoyed is permanent. The payoff is bigger than space weather. Systems that admit uncertainty fail softer everywhere. A constellation that scrubs and staggers survives parts hiccups and ground chaos. A grid that drills black start bounces back from storms and software. An airline that keeps raw data skills alive rides through interference and runway closures. Resilience multiplies. And the awe stays. We don't defeat a planet, we coordinate with it. The dent isn't the enemy. It's the constraint that makes craftsmen. They learn the beat of 2 drifting rooms, the seasons of storms, the slow pulse of a lumpy earth. They draw calendars that look like weather, practice to boredom, and deliver quiet days on loud nights. That's not a step down. That's how we stay in the game. Keep the maps breathing, fund the satellites and observatories that turn drift into guidance. Keep models honest and usable. Tools, not talismans. Teach the next class that uncertainty isn't an error. It's the medium. We fly to see, wire to share, and measure, because the planet won't hold still. Fragile tech on a wild planet isn't a tragedy. It's the only way we ever get to play. Earth's shield isn't dying, it's shifting, and our tech has to act like it lives here. A hot mantle lid nudges core flow. The core redraws lines. We plan routes, harden boards, and rehearse until the worst day looks routine. Want the solar side? The storms that turn dents into tests? Watch the next episode. If your job depends on the blue dot, a flight plan, or a steady grid, subscribe for more true science playbooks and send this to the person who writes your rules.